All right, Math 1 folks, quick review here of the quiz. This is sort of part 2 of the quiz we started last week. The key here in question 3 here is about percentage growth. So recall that when we say 6% growth, that means 0.06, so we have to do that translation. And we have to remember that this means a growth means that's over 100%. So we say everything that we had before and then 6% more. So 100% is what we have times 1, and 6% means 0.06. So we're going to have everything times 1.06. Another way to think about this is to say, okay, so our input here is going to be hours, and our output. So we could say starts out with bacteria. So before any growth, we could say at hour 0. That would be fine. If you use hour 1, that's also acceptable, but you're going to have to make sure that you're very careful about the function and how you write the function. Anyway, our output here is bacteria. And it says it starts out with 2,000, so it's 2,000. And then the first hour, after 1 hour, we have 2,000 times 1.06. So, just another way of explaining this. When we say it grows by 6%, that means it's more than times 1. If I just said 2,000 times 1, that would be 100%, right? Because 1 is 100%. So 100% of 2,000 is 2,000. 100% of that is 2,000. And 100% of that is 2,000. So obviously we just multiply by 1. It's not going to be enough. It has to be more than 1 for it to get bigger. And so 6% means this much more than 100%. 6% growth. So with 106% more than 100% is 106%. So that's 1.06. So I have 1.06, so 2,000 times 1.06. 2,000 times 1.06, that is 2120. Okay. And then the second one times 1.06 is 2247.2. Okay, so this column right here, this is going to be the actual number of bacteria. And then I'm going to show here how I got that. Well, I got that by taking the previous number and multiplying it by 1.06. And I got that previous number by taking 2,000 and doing 1.06. So here is our principle of recursion. Over and over again, the same thing. So it's 2,000 times 1.06 got us to here, times 1.06 got us to here. So this means this is 2,000 times 1.06 to the second power. So third hour, 2,382. 0.032. So 0.032, we can just say 0.0. That's close enough. I'm going to keep this in my calculator so I make sure I don't get off, because I don't round it when I'm actually doing the calculations. But for just showing it, that's fine. So this is 2,000 times 1.06 times 1.06 times 1.06. To the third. So this is going to be times 1.06 to the fourth, because we're going to multiply it again. This is 2524.95, so 2525, just about. All right. So this one, I multiplied it by 1. So if we look at this pattern, we can see, oh, this was 2,000 times 1.06 to the first power. That means this is 2,000 times 1.6 to the 0 power, to the power of 0, meaning there were 0 1.6s, right? We didn't multiply it at all. So we can see our function here is anytime we have an x, what we write is 2,000 And then we multiply it by 1.6 a certain number of times. That number of times is the same as the number of hours. So I say that the x. So this is our function. F of x equals 2,000 times 1.06. Now this says how many bacteria will there be in 6 hours. And on this table, yeah, you could just keep going. But what if it said more hours than that? That's what you're going to want to be able to do, because on the quiz, there's no telling, is it going to be 6 or 16? So once we have our function here, that allows us to say, okay, well, it's 6 hours. What's f of 6? What is the function output when my input value, hours, is 6? Well, it's going to be 2,000 times 1.06 to the 6th power. Right? We'd have to, 6 times we have to multiply it by 1.06. 2,000 times 1.06 to the 6th power. That gives me 2,837.03825, so just about that. That's good enough. Okay, we could say 0.04 if you wanted. I'm not concerned about your rounding. In this step, I would be concerned, and you could lose points if you rounded somewhere up here. So that's our how many bacteria there'll be in 6 hours. So this is going to be 2837. If I take this one, 4.95 times 1.06, that gives me 2676. And now I've got graph the data so that all 7 rows are represented. So I've got 0, 1, 2, 3, 4, 5, 6. So there are 7 rows, 0 through 6. Here's my 0. So it makes sense for me to count it by 1, 2, 3, 4, 5, 6. Yeah, I don't have 7, 8, or 9. But if I counted by 2s, I'd run out of room. Or it'd be too small. If I said 1, 2, 3, 4, I'd be out of room. If I went 2, 4, 6, 8, then before half of the graph was done, I'd already be used up all my data. So I don't want that. And then I've got all my data right here. So it's just a matter of putting it on the graph. Here is, we know we start at 2,000, but we don't want to call this 2,000 because this looks like a y-axis. So we want to make sure that we're accurately showing that we already start with a certain number of bacteria and then it grows at a slower rate. So I've got to get from 2,000, well, from 0, then we know we're going to start at 2,000, and then that means we're going to have to get all the way up to 2,837. Now, I'm looking at 1, 2, 3, 4, 5, 6, 7, 8, 9 grid lines. 9 grid lines. So I'm going to see what can I count by. 1, 2, 3, 4, 5, 6, 7, 8, 9. What can I count by? So that in 9 grid lines, I'm going to reach this. Well, let's see. If I do 9 grid lines, if I do 2837 divided by 9, that's 315. So that means if I count by 315, I'd get exactly up to 2,837, right? But I don't know how to count by 315s very easily. That's a lot of mental work. I want a nice round number. So if I count it by 300, and I have 9 grid lines, that gets me to 2,700. Now 2,700 really isn't enough to incorporate this one. So realistically, I probably need to get higher than that. So if I said 3,000 divided by 9, well, now I'm getting 333. So a couple of options. I could say, well, I happen to know that that means every third line, 1, 2, 3, is 1,000. Right, so I could, I'm just going to show this here. I could say, okay, here's 1,000, here's 2,000, here's 3,000. And I know that this is about 333, and this is about 667. Maybe a little awkward to work with here, but at least I've got thousands like that. Or I could count by 350 times 9 grid lines. That gets me to 3150. Counting by 350 feels a little awkward, right? I'd go 350, 700. But I think I can manage that. The other thing is I could count by 400s. That would bring me up to 3,600. So 3,600, quite a bit higher than this. So there's not a single right answer. If I counted by 500s, it'd probably be too small. If I counted by 300s, I'd run out of room. I'm going to count by 350s. I happen to think in my head, well, 350 times 2 is 700. And being somewhat of a football fan, I could say I know my multiples of 7. This is going to be 1,400. This is going to be 2,100. This is going to be 2,800, that's handy to have 2,800 because this is pretty close to that. Okay, so then my 0 starts at 2,000. Now this is where we kind of get into trouble. Okay, from 1,400 to 2,100, this is going to be 1,750. So where is 2,000 in that? Well, I'm going to say it's about right there. That's about as accurate as I'm going to get. So, and then 1, it goes up to 2,120, so just barely above this line. And then it goes to 23. So 2 is about there. 3 is closer to there, so I think this is 2. 4 is about 25. 25. 5 is 26. 76. And 6 is 2837. That's a really gentle curve, but it is a curve. It's not straight. And that's what I'll be looking for on your quiz. Can you show me that it's actually a curve? All right, part 2 of this review is this one. We've gone over this actually problem in warm-ups a couple days. So we need to find the common factor. That is 80,000 times what equals 82,000. What's the multiplier here? We can use any letter. I'm just going to use R to solve this. So this is 82,000. And so R is going to be 82,000 divided by 80,000. Which gives me 1.025. 1.025. And now it asks me for the percentage growth. So there are a number of ways we could reason through this. But I'm going to do it this way. 1.025, if that is a decimal, I want to figure out what is that as a percentage. So I move the decimal over 2 places, multiply by 100. And this is 102.5%. So recall from what we said earlier that 100% of 80,000 would be 80,000. So if I made a second column, and then what would be 100%? Not 100% growth, but 100% of 80,000 would be 80,000, and 100% of that would be 80,000, right? So 100% of gives us the same thing. We want more than 100%. So this is 2.5% more than 100%. As in, it's not just staying the same. It's not just times 1. It's times a little bit more than 1. And so this is what we'd call it. 2.5% growth. Number 6, the health department finds the number of flu cases is doubling. What's the common factor? Well, we have to just think about what, in any scenario, if we say something is doubling, that means that it's times 2, so the common factor would be 2. Now the percentage growth means 2 is 200%. How much more is this than 100%? This is 100% more than 100%. So we're at 100% growth. James, find the common factor of sequence is 7.75. Is this sequence increasing or decreasing? Well, you could just try it out. You could say, okay, well, what's 100 times 0.75? And, oh, it's going down. So we'd say this is decreasing. By what percentage? So again, we say, okay, this is 0.75%, or 0.75. That's the same as 75%. Compare that to 100%. And what do we see? It's 25% less than 100%. So we say it's a 25% decrease. All right. So there's your review for the quiz. I hope this helps, and we will see you in class when you're taking it. I believe if you work hard and you study, you'll be able to do really well.